In 1988, divers exploring the Mediterranean seafloor made a discovery that would eventually become crucial to understanding the fundamental nature of reality. What they found wasn't gold or precious artifacts, but something far more valuable to modern science. Over 30 metric tons of ancient Roman lead that had been aging underwater for 2 millennia. Today, that same lead shields the XENON dark matter detector, hunting for particles that make up roughly 85% of the universe's matter yet remain completely invisible. These experiments could explain why the universe didn't annihilate itself 13.7 billion years ago. But the story of how this underwater treasure became essential to modern physics begins with what appeared to be just another Mediterranean shipwreck, the discovery that changed everything. 28 meters below the Mediterranean surface off Sardinia, the diving team initially thought they had found another routine Roman wreck. The scattered pottery fragments looked familiar enough, spread across the sandy bottom in the predictable pattern of a ship that had broken apart centuries ago. But as they swam closer to examine the site more carefully, something felt wrong. The debris field was massive, far larger than what they expected from a typical merchant vessel of the era. As the archaeological team began their systematic excavation, the true nature of this discovery started to emerge. Beneath layers of sediment and marine growth, they uncovered the first of what would prove to be an extraordinary cargo. These weren't the typical trade goods of olive oil, wine, or grain that filled most Roman merchant ships. Instead, they found carefully shaped rectangular blocks, each one weighing approximately 33 kilograms and measuring about 40 centimeters in length. The excavation process revealed just how massive this cargo really was. Each day brought more ingots to light, and the numbers quickly became staggering. The archaeological team realized they were looking at over 1,000 individual lead blocks, representing more than 30 metric tons of processed metal. This wasn't just unusual for a Roman cargo ship. It was unprecedented. No other Mediterranean wreck had ever yielded anywhere close to this quantity of lead in a single shipment. Each ingot told its own story through the inscriptions cast into the lead during the original smelting process. The markings revealed a sophisticated Roman industrial network that spanned the empire. Some ingots bore the names of Roman lead mines in Britain. Others showed processing marks from smelters in Spain and Gaul. The stamps indicated quality grades, weights, and even the names of Roman officials who had overseen the production. This wasn't local metalwork. It represented a complex supply chain that brought lead from mines across the empire to a central processing location. The mystery of the ship's intended destination proved more elusive. Roman records from the period show massive construction projects throughout the empire that would have required enormous quantities of lead for plumbing, roofing, and architectural elements. The ship could have been heading to Rome itself, where lead was constantly needed for the growing city's infrastructure. Alternatively, it might have been bound for one of the major provincial capitals undergoing expansion during the height of Roman power. What caused the ship to sink remained equally mysterious. The waters off Sardinia were known for sudden storms that could overwhelm even well-built vessels. The island's name, Mal de Ventre, likely derived from the Sardinian phrase meaning bad winds, suggesting that treacherous weather was a constant threat in these waters. With such massive cargo weighing down the hull, the ship would have been particularly vulnerable to rough seas. A single large wave might have been enough to flood the holds and send the entire vessel to the bottom. The underwater environment had created perfect preservation conditions for the lead cargo. While the ship's wooden structure had largely decomposed over 2 millennia, the lead ingots remained virtually unchanged. The cold, oxygen-poor conditions at 28 meters depth prevented the oxidation that would have corrupted the metal if it had been buried on land. The steady temperature and lack of significant currents meant the ingots had been sitting in essentially the same positions where they had settled when the ship broke apart. This preservation proved crucial for reasons the original Roman merchants could never have imagined. Lead naturally contains trace amounts of radioactive isotopes, but these decay over time according to predictable half-life schedules. The underwater environment had not only preserved the physical integrity of the ingots, but had also allowed the natural radioactive decay process to continue undisturbed for 2,000 years. This meant the Roman lead now contained significantly lower levels of radioactive contamination than any lead processed in the modern era. As archaeologists continued their painstaking documentation of the find, they began to realize this discovery transcended normal archaeological significance. The sheer quantity and exceptional preservation of the lead made it potentially valuable for applications far beyond historical research. Modern industries that required extremely pure, low-radiation materials had few sources available. Most contemporary lead contained radioactive isotopes introduced during the Industrial Age, particularly after atmospheric nuclear testing began in the 20th century. Word of the discovery began to spread beyond archaeological circles. Materials scientists and physicists learned about the existence of 30 tons of pre-industrial lead with exceptionally low radioactive content. For researchers working on experiments that required the most sensitive detection equipment imaginable, this ancient Roman cargo represented an opportunity that might never come again. The lead's 2,000-year aging process had created something that modern industry simply could not replicate. The intersection of archaeology and modern physics was about to create one of the most unusual collaborations in scientific history. These Roman ingots would eventually find their way to a laboratory buried 1.4 kilometers beneath solid rock in the Grand Sasso mountain range of Italy. There, shielded from cosmic radiation by both ancient lead and massive stone, scientists would use this cargo to hunt for answers to questions that wouldn't even be formulated for another 2 millennia after the ship sank. This ancient lead was about to help solve a puzzle that threatened the very existence of everything we know. The Romans had unknowingly preserved the key to understanding why anything exists at all. The cosmic mystery that shouldn't exist. The universe has a problem that should have prevented everything from existing in the first place. According to our best understanding of physics, the Big Bang should have produced exactly equal amounts of matter and antimatter. When these two forms of matter meet, they don't just cancel each other out. They annihilate completely, converting all their mass into pure energy in a brilliant flash of light. If the mathematics of the early universe worked the way our equations predict, you wouldn't be here. Neither would Earth, the Sun, or any of the billions of galaxies scattered across space. The entire cosmos should be nothing but empty darkness filled with the fading radiation from the greatest explosion that never should have left anything behind. The standard model of particle physics lays out this cosmic death sentence with mathematical precision. When the universe began 13.7 billion years ago, the tremendous energy of the Big Bang should have created matter and antimatter in perfectly balanced quantities. Every proton paired with an antiproton. Every electron matched with a positron. Every neutron accompanied by an antineutron. The symmetry appears fundamental to how particles behave at the quantum level, and yet the symmetry should have doomed the universe to immediate self-destruction. The annihilation process itself is both elegant and terrifying in its efficiency. When a particle encounters its antimatter twin, the collision releases energy according to Einstein's famous equation. The mass of both particles converts entirely to electromagnetic radiation, typically in the form of gamma rays. This isn't a chemical reaction where atoms rearrange themselves. This is complete obliteration at the most fundamental level possible. The particles simply cease to exist, leaving only their energy signature behind as proof they were ever there. But the universe clearly didn't annihilate itself. Stars burn across the night sky. Planets orbit in stable patterns. You exist to contemplate this mystery. Something went wrong with the cosmic balance sheet, and that something represents one of the most profound puzzles in modern physics. The mathematical impossibility of our existence suggests that either our understanding of the early universe is fundamentally flawed, or some unknown process created a tiny but crucial asymmetry in the first moments after the Big Bang. The Planck satellite has measured this cosmic imbalance with extraordinary precision. The baryon to photon ratio stands at approximately 6.1 times 10 to the negative 10th power. This number represents how many matter particles exist compared to the photons left over from the Big Bang's radiation. The measurement reveals that for every billion matter-antimatter pairs that should have annihilated each other in the early universe, somehow one extra matter particle survived. This represents a difference of just 1 part in a billion, but that microscopic advantage was enough to populate the entire observable universe with matter. The precision required for this imbalance staggers the imagination. If the ratio had been even slightly different, we might be living in a coma state. Universe with no matter at all. Or conversely, one where the cosmic microwave background radiation would look entirely different. This tiny asymmetry allowed every atom in your body, every star in the sky, and every planet orbiting those stars to exist instead of vanishing in the first moments after creation. Several theories attempt to explain how this asymmetry could have emerged from an initially symmetric state. Electroweak baryogenesis suggests the imbalance arose during a specific phase transition in the early universe when the fundamental forces were still unified. During this period, the universe underwent dramatic changes in temperature and energy density that might have created conditions favoring matter over antimatter production. The process would have required precise timing and specific particle interactions that remain largely theoretical. Inflationary cosmology adds another layer of complexity to the puzzle. The rapid expansion of space during the universe's first fraction of a second might have created conditions where quantum fluctuations could establish lasting asymmetries. During inflation, the universe grew by an enormous factor in an incredibly short time, potentially stretching quantum scale imbalances into macroscopic differences that persisted after the expansion slowed. Recent research has explored even more exotic possibilities. The LHCb experiment at CERN has provided new insights into fundamental asymmetries in particle behavior. The experiment revealed that baryons, the family of particles that includes protons and neutrons, exhibit subtle differences in their behavior compared to their antimatter counterparts. These discoveries offer new ways to understand why elementary particles follow the patterns described by the Standard Model, and why matter apparently won the cosmic battle against antimatter. Understanding this cosmic asymmetry represents far more than academic curiosity, the solution to the matter. Antimatter puzzle could revolutionize our understanding of fundamental physics and reveal new laws of nature that operate under the most extreme conditions imaginable. The answer might require us to abandon cherished assumptions about symmetry and conservation laws, or it might point toward new particles and forces that remain hidden since the universe began. The experiments designed to solve this mystery require the most sensitive detection equipment ever built. They must measure processes so rare and subtle that even the tiniest contamination from background radiation can overwhelm the signals scientists hope to detect. These experiments need shielding materials with radioactive contamination levels lower than anything found in the modern world. They need materials that have been isolated from cosmic rays and nuclear fallout for centuries or millennia. The answer might lie in studying particles so elusive that they can pass through entire planets without leaving a trace. Ghosts in the machine. These particles have earned their reputation as the ultimate escape artists of the subatomic world. Right now, as you read these words, approximately 100 billion neutrinos are streaming through every square centimeter of your body each second. These particles move at nearly the speed of light, arriving from the sun, from distant supernovas, and from the cosmic radiation that fills the universe. You can't feel them, see them, or detect them in any way with your senses. They pass through you as if you weren't even there, continuing their journey through the Earth and out into space without slowing down or changing direction. Neutrinos earned their nickname as ghost particles because they interact so weakly with ordinary matter that they can travel through entire planets without hitting a single atom. While other particles collide and scatter when they encounter even thin materials, neutrinos pass through lead walls, steel barriers, and miles of solid rock as easily as light passes through clear glass. The entire Earth presents no more obstacle to a neutrino than a sheet of tissue paper presents to a rifle bullet. The properties that make neutrinos so elusive also make them incredibly abundant. The universe produces them in staggering quantities through nuclear reactions in stars, radioactive decay processes, and cosmic ray interactions with the atmosphere. Every second, about 65 billion neutrinos from the Sun alone pass through each square centimeter of the Earth's surface. Yet despite this constant bombardment, detecting even a single neutrino requires enormous experimental apparatus and extraordinary patience. Scientists predicted the existence of neutrinos in 1930 to solve a puzzle in radioactive decay, but actually catching one took another 26 years. The first successful detection required a massive underground detector filled with hundreds of gallons of cleaning fluid, positioned near a nuclear reactor that produced trillions of neutrinos every second. Even with this intense source, the detector registered only a few neutrino interactions per hour. The experiment proved that neutrinos existed, but it also demonstrated just how challenging these particles would be to study. The fundamental challenge of neutrino detection stems from the weakness of the interactions that govern their behavior. While electrons and protons participate in electromagnetic interactions and respond to electric and magnetic fields, neutrinos only interact through the weak nuclear force. This force operates over incredibly short distances and involves probability calculations rather than the certainty that governs other particle interactions. A neutrino has roughly a 50% chance of interacting with matter only after traveling through a light year of solid lead. Modern neutrino detection requires facilities that dwarf the early experiments. Underground laboratories house detectors containing thousands of tons of specialized materials designed to maximize the chances of capturing a neutrino interaction. These detectors use water, liquid scintillator, or noble gases as target materials, surrounding them with thousands of sensitive light detectors that can register the faint flashes produced when a neutrino finally collides with an atomic nucleus. The 2025 advances in neutrino detection technology have pushed sensitivity to unprecedented levels. The XENON experiment at Grand Sasso National Laboratory uses 5.9 metric tons of liquid xenon as its detection medium, representing a dramatic increase in scale compared to earlier experiments. This detector achieves sensitivity improvements of almost 4 orders of magnitude compared to its predecessor, meaning it can detect interactions that are 10,000 times rarer than what previous experiments could observe. The technical challenges of building such sensitive detectors extend far beyond simply scaling up the size. Each component must be manufactured from materials with extremely low levels of radioactive contamination. Every surface that comes into contact with the detection medium must be cleaned to remove trace amounts of radon, uranium, and other naturally occurring radioactive elements. Even the metal parts of the detector housing must be fabricated from specially selected materials that have been screened for radioactive purity. Current neutrino experiments are also sensitive to interactions with dark matter particles, expanding their scientific reach beyond neutrino physics alone. When dark matter particles collide with a xenon nuclei in detection experiments like XENON, they produce signals that can be distinguished from neutrino interactions through careful analysis of the energy and timing patterns. This dual capability makes modern neutrino detectors powerful tools for exploring multiple aspects of fundamental physics simultaneously. The experimental challenges of studying these ghost particles push detection technology to its absolute limits. Measuring neutrino properties requires detecting the tiny energy differences in particle interactions. Differences so small that they're overwhelmed by any background radiation or thermal noise in the detector. These measurements demand shielding materials with radioactive contamination levels lower than anything available in the modern industrial world. The convergence of neutrino research with dark matter detection creates opportunities for discoveries that could revolutionize our understanding of reality. The ghost particles that stream invisibly through your body every second might provide crucial insights into the fundamental structure of matter and energy. But capturing these elusive interactions requires experimental conditions so pristine and isolated that scientists must literally hide from the universe itself to achieve them. The underground Cathedral of Science. Beneath the Apennine Mountains in central Italy, scientists have carved out one of the most extraordinary research facilities on Earth. The Grand Sasso National Laboratory sits nearly a mile underground, accessible only through a highway tunnel that cuts directly through the mountain's heart. What began as an engineering project to connect Rome with Italy's eastern coast has become the gateway to humanity's deepest scientific frontier. The laboratory's entrance resembles nothing more than a highway rest stop, but beyond those unremarkable doors lies a complex of chambers that house some of the most sensitive scientific instruments ever constructed. The underground complex spans over 180,000 cubic meters of excavated space, divided into 3 massive experimental halls that dwarf most cathedral interiors. Each hall rises to heights of 100 meters or more, their vaulted ceilings disappearing into shadows that electric lighting can barely penetrate. The scale becomes apparent only when you spot the tiny figures of scientists moving between towering detector assemblies that reach from floor to ceiling. These spaces were designed not for worship, but for the pursuit of knowledge about the fundamental nature of reality. The mountain itself provides the laboratory's most crucial feature, 1,400 meters of solid rock that shields the experiments from cosmic ray bombardment. Every second, cosmic rays from deep space strike Earth's atmosphere, creating cascades of particles that rain down on the planet's surface. While these particles pose no danger to human health, they create an overwhelming background noise that would make sensitive physics experiments impossible. The Grand Sasso facility reduces cosmic ray interference by a factor of 1 million compared to surface conditions. This extreme shielding represents only the beginning of the isolation these experiments require. Inside the mountain, scientists have constructed additional layers of protection around their most delicate instruments. The XENON experiment, housed in Hall B, sits within multiple nested shields that block different types of radiation. The outermost barrier consists of a water tank containing 700 tons of ultra-pure water, followed by layers of polyethylene and lead shielding. Each material blocks specific types of particles that can interfere with the experiment's measurements. The XENON detector itself represents the pinnacle of detection science. This massive instrument uses 5.9 tons of liquid xenon as both target material and detection medium. When a particle interacts with a xenon nucleus, it produces both light and electrical signals that sensitive photodetectors can measure. The detector contains 494 photomultiplier tubes, each capable of detecting individual photons. The entire assembly operates under conditions more extreme than anything found naturally in the cosmos. The construction of these detectors demands materials with radioactive contamination levels far below anything found in normal manufacturing. Every component undergoes screening to measure its natural radioactivity. Stainless steel parts are selected from batches with the lowest possible uranium and thorium content. Even the photomultiplier tubes are manufactured using specialized glass formulations that minimize radioactive impurities. The detector assembly takes place in clean rooms with filtered air systems that prevent radon contamination during construction. But even these precautions aren't sufficient for the XENON experiment's requirements. The detector needs shielding materials with radioactive contamination levels lower than anything available in the modern industrial world. Contemporary lead contains radioactive isotopes introduced during the industrial age, particularly after atmospheric nuclear testing began in the 20th century. These trace amounts of radioactivity would overwhelm the faint signals that scientists hope to detect. This is where the ancient Roman cargo becomes essential to 21st century physics. The lead ingots recovered from the Mediterranean seafloor have been aging underwater for 2 millennia, allowing their natural radioactive isotopes to decay to levels far below modern materials. The cold oxygen-poor conditions at 28 meters depth prevented oxidation while allowing the radioactive decay process to continue undisturbed. This underwater preservation created lead with contamination levels that modern industry simply cannot replicate. The Roman lead now forms crucial components of the XENON detector's shielding system. The ancient metal blocks gamma rays and other forms of radiation that can mimic the signals produced by dark matter interactions. Without this ultra-pure shielding material, the experiment would be unable to distinguish genuine dark matter events from background radiation. The 2,000-year aging process that began when the Roman ship sank has made possible one of the most sensitive physics experiments ever attempted. The XENON experiment represents a 5-fold improvement in background suppression compared to its predecessor, Xenon 1T. This enhanced sensitivity allows scientists to probe interactions that are 5 times rarer than what previous experiments could detect. The improvement stems partly from the detector's increased size and partly from advances in shielding technology, including the use of the ancient Roman lead. International collaboration drives every aspect of these underground projects. The XENON experiment involves over 200 scientists from 40 institutions across the globe. Teams from Germany design and build the detector's central components, while groups from the United States provide specialized electronics and data analysis systems. Italian researchers coordinate the facility operations and provide expertise in underground construction techniques. The delicate nature of these experiments becomes apparent when you consider their sensitivity requirements. The XENON detector can register interactions involving single particles, measuring energy deposits as small as a few electron volts. This sensitivity makes the experiments vulnerable to interference from sources that would be completely undetectable by human senses. The slightest contamination or thermal fluctuation could compromise years of data collection. The facility's isolation extends beyond protection from cosmic rays. The underground location shields experiments from electromagnetic interference that pervades the surface world. Radio transmissions, cell phone signals, and electrical power systems all produce electromagnetic fields that could interfere with sensitive measurements. The mountain's natural shielding blocks these signals, creating an environment of electromagnetic silence that exists nowhere on Earth's surface. These hidden laboratories represent humanity's most ambitious attempt to understand reality itself. But achieving the sensitivity required for dark matter detection demands more than just isolation from radiation and electromagnetic interference. The experiments must operate under temperature conditions that push the boundaries of what space reaches temperatures of approximately 2.7 Kelvin above absolute zero, cold enough to freeze any known substance instantly. But scientists working with the XENON experiment have created conditions significantly colder than the vacuum between stars. XENON keeps 5.9 tons of xenon at minus 95 degrees Celsius, using advanced refrigeration, a key innovation that modern materials alone couldn't achieve. This artificial environment represents one of the coldest sustained temperatures ever achieved on Earth, maintained continuously for years while scientists hunt for the universe's most elusive particles. The XENON detector houses 8.6 tons of xenon in various states, with 5.9 tons kept in liquid form within the active detection chamber. Maintaining xenon in its liquid state at these extreme temperatures requires a sophisticated cryogenic system that operates with precision measured in thousandths of a degree. The cooling apparatus consumes enormous amounts of electrical power, running continuously to prevent even momentary temperature fluctuations that could compromise the experiment's sensitivity. The engineering challenges of achieving these temperatures begin with the fundamental properties of xenon itself. This noble gas naturally exists as vapor at room temperature and pressure, requiring careful manipulation to condense into liquid form. The process involves multiple stages of compression and cooling, each step demanding specialized equipment designed to handle the extreme conditions. The xenon must be purified to remove even trace amounts of radioactive impurities before cooling, as any contamination becomes concentrated and more problematic at low temperatures. Detecting dark matter particles requires these extreme conditions because thermal motion at higher temperatures creates background noise that overwhelms the faint signals scientists hope to measure. At room temperature, xenon atoms vibrate constantly due to thermal energy, producing random electrical signals that obscure the tiny pulses generated by potential dark matter interactions. Cooling the xenon to near absolute zero slows these atomic vibrations to almost nothing, creating the quiet environment necessary to detect single particle collisions. The detector's sensitivity approaches the theoretical limits of what physics allows. When a dark matter particle theoretically collides with a xenon nucleus, it transfers only a few thousand electron volts of energy, an amount so small that it gets lost in thermal noise at normal temperatures. The extreme cold ensures that any energy deposit above this threshold represents a genuine particle interaction rather than random thermal fluctuation. This sensitivity allows the experiment to detect interactions involving individual atoms within the multi-ton xenon target. The XENON experiment uses a dual-phase time projection chamber design that requires precise control of both liquid and gaseous xenon phases simultaneously. The detector maintains a thin layer of xenon gas above the liquid surface, with the boundary between phases controlled to within millimeters. This interface must remain stable despite the constant cooling and any vibrations that might affect the system. The engineering tolerances required for this stability exceed those used in spacecraft construction or precision manufacturing. Particle interactions within the liquid xenon produce both light and electrical signals that sophisticated detection systems must capture and analyze. The light signals consist of individual photons produced when xenon atoms return to their ground state after being excited by particle collisions. The electrical signals result from ionization, where particle impacts strip electrons from xenon atoms. Both types of signals occur within nanoseconds of the original interaction, requiring the electronics capable of responding faster than any human reaction time. The detector contains 494 photomultiplier tubes arranged in arrays above and below the xenon chamber. These devices amplify single photons into electrical pulses large enough for electronic systems to process. Each photomultiplier tube operates at the same extreme temperature as the xenon target, requiring specialized designs that maintain sensitivity while subjected to conditions that would destroy normal electronic components. Maintaining these conditions for extended periods presents ongoing challenges that require constant attention from teams of scientists and engineers. The cooling systems operate under tremendous stress, with mechanical components subjected to thermal cycling and pressure changes that can cause failures without warning. Backup systems stand ready to maintain temperature if primary cooling fails, but even brief temperature excursions can require weeks of stabilization before data collection can resume. The facility's power requirements reflect the energy cost of fighting thermodynamics. The refrigeration systems consume several hundred kilowatts of electrical power continuously, enough to supply dozens of homes. This energy consumption represents a significant operational expense that must be sustained for years to collect sufficient data for meaningful scientific analysis. Emergency power systems ensure that cooling continues even during electrical outages that might last for hours. Quality control for the cryogenic systems involves monitoring thousands of parameters simultaneously. Pressure sensors track the xenon vapor pressure throughout the chamber. Flow meters measure the circulation rates of cooling fluids. Temperature sensors provide continuous feedback for automatic control systems that adjust cooling rates in real time. This monitoring generates enormous amounts of data that automated systems analyze for signs of developing problems. The XENON collaboration has developed specialized techniques for purifying xenon to the extreme levels required for dark matter detection. The purification process removes radioactive contaminants down to parts per trillion, concentrations so low that they approach the limits of analytical chemistry. Even teeny amounts of radioactive impurities would overwhelm the detector's sensitivity, making this purification essential for experimental success. This artificial environment is more extreme than anything found naturally in the cosmos. Yet even these extraordinary conditions weren't enough to solve the fundamental challenge that threatened to make the entire experiment impossible. The mountain itself was working against him. The radiation problem. Background radiation infiltrated every corner of the underground laboratory, creating a constant stream of false signals that threatened to drown out the faint whispers of dark matter interactions. Even with 1,400 meters of solid rock overhead and multiple layers of specialized shielding, the XENON experiment faced an enemy that seemed impossible to escape. The scientists had assumed that burying their detector beneath an entire mountain would solve their radiation problems, but they quickly discovered that radioactivity found ways to infiltrate even the most protected environments. The omnipresent nature of this threat became apparent during the experiment's early calibration phases. Radiation detectors throughout the facility registered constant activity from sources that proved nearly impossible to eliminate. The concrete walls of the underground chambers contained trace amounts of uranium and thorium that had been present in the original construction materials. The steel framework supporting the detector assemblies carried radioactive isotopes absorbed during the manufacturing process. Even the air circulating through the laboratory contained radon gas that seeped from the surrounding rock, creating a persistent source of contamination. The sensitivity requirements of dark matter detection experiments mean that even microscopic amounts of radioactivity can overwhelm the signals scientists hope to measure. A single radioactive decay event within the detector's sensitive volume produces thousands of times more energy than a theoretical dark matter interaction. The XENON detector can register energy deposits as small as a few electron volts, but radioactive contamination typically produces signals measuring thousands or tens of thousands of electron volts. This difference in scale means that just a few radioactive atoms within the detector's xenon target can generate enough false signals to mask genuine dark matter events completely. Modern lead presented the most frustrating obstacle to achieving the background levels required for dark matter detection. All recently mined lead contains measurable amounts of lead-210, a radioactive isotope with a half-life of 22.3 years that creates exactly the type of background signals that interfere with sensitive particle physics experiments. This isotope forms naturally as uranium decays in or deposits, becoming incorporated into lead during the mining and smelting process. The 22-year half-life means that even lead processed decades ago still contains significant amounts of this contaminant, making it unsuitable for experiments that require detecting individual particle interactions. The precision requirements of modern particle physics experiments have pushed material purity standards far beyond what other scientific disciplines require. While analytical chemistry might consider materials pure, when contaminants measure parts per million, dark matter experiments need contamination levels measured in parts per trillion or even parts per quadrillion. Achieving these purity levels with modern materials requires specialized processing techniques that often prove more expensive than the experiments can afford, and even then, the results rarely meet the stringent requirements for ultra-low background detection. Cosmic ray interactions create ongoing contamination problems that affect all materials exposed to the Earth's surface. High-energy particles from space constantly bombard the atmosphere, creating cascades of secondary particles that reach the ground and interact with materials in ways that produce radioactive isotopes. These cosmic ray spallation products accumulate in materials over time, with the contamination levels depending on how long the materials have been exposed to cosmic radiation. Materials that spend years or decades at the Earth's surface acquire measurable amounts of cosmogenic isotopes that make them unsuitable for sensitive physics experiments. The search for suitable shielding materials led scientists to explore sources that most people would never consider for high-tech applications. Archaeological sites offered materials that had been isolated from cosmic rays for extended periods, allowing cosmogenic isotopes to decay to undetectable levels. Underwater locations provided natural shielding from cosmic radiation while preserving materials in chemical states that minimized contamination. The ideal materials would have been isolated from cosmic rays for decades or centuries while remaining chemically stable and suitable for processing into modern shielding components. Ancient Roman lead offered a unique solution to the contamination problem that modern materials simply could not match. The lead ingots recovered from the Mediterranean seafloor had been aging underwater for 2 millennia, allowing their natural radioactive isotopes to decay to levels far below anything achievable with contemporary materials. The 22-year half-life of lead-210 meant that this contaminant had undergone nearly 90 complete decay cycles during the 2,000 years the ingots spent on the ocean floor. The underwater environment provided natural shielding from cosmic rays while preventing the accumulation of new radioactive isotopes that would contaminate materials exposed to the surface environment. The cold, oxygen-poor conditions at 28 meters depth had preserved the Roman lead in a pristine state while allowing the radioactive decay process to continue undisturbed. This underwater preservation created lead with contamination levels that modern industry simply cannot replicate, regardless of the purification techniques employed. The ancient metal blocks gamma rays and other forms of radiation that can mimic the signals produced by dark matter interactions, providing shielding capabilities that would be impossible to achieve with contemporary materials. Quality control measurements confirmed that the Roman lead contained radioactive contamination levels orders of magnitude lower than the best modern alternatives. Specialized detector systems with measurement periods lasting weeks were necessary to characterize these ultra-low contamination levels, and the results consistently show that the ancient material met the stringent requirements for dark matter detection experiments. The 2,000-year aging process that began when the Roman ship sank had created something that 21st century technology could not duplicate. The realization that archaeological artifacts could provide crucial materials for cutting-edge physics experiments created an unprecedented situation. Scientists who had spent their careers studying the universe's most fundamental particles suddenly found themselves needing expertise in maritime archaeology and ancient metallurgy. The intersection of these vastly different fields would require collaborations that had never existed before. When archaeology meets physics, the moment arrived when particle physicists realized their expertise in detecting the universe's most elusive particles was useless without becoming amateur treasure hunters. The XENON collaboration faced an impossible challenge. They needed shielded materials with radioactive contamination levels that simply didn't exist in the modern industrial world. Every supplier they contacted offered lead that contained too much background radiation to make their experiment work. The solution would require them to abandon conventional procurement methods and start thinking like archaeologists searching for artifacts that had been isolated from cosmic radiation for centuries. The concept of low background ancient materials represents a complete reversal of how most people think about purity and contamination. In normal circumstances, newer materials are cleaner and more refined than older ones. But the physics of radioactive decay creates a situation where age becomes the most valuable property a material can possess. Lead processed from or a century ago contains radioactive isotopes that are still decaying and producing the exact type of interference that ruins dark matter detection experiments. The same lead, if it had been sitting underwater for 2,000 years, would have had time for these isotopes to decay to undetectable levels. Underwater preservation creates nearly perfect conditions for producing the ultra-clean materials that modern physics experiments require. The ocean shields submerged objects from cosmic rays that would otherwise create new radioactive isotopes through nuclear reactions. The constant temperature and chemical environment prevent the types of contamination that occur when materials are exposed to varying atmospheric conditions. Most importantly, the underwater environment isolates materials from the industrial processes that have introduced artificial radioactivity into the modern world since the beginning of the nuclear age. The serendipitous timing of the 1988 Roman shipwreck discovery off Sardinia and the experimental needs of the XENON collaboration created an opportunity that seemed almost too perfect to be coincidental. The divers found the wreck just as particle physicists were beginning to understand the extreme purity requirements for dark matter detection experiments. The shipwreck contained exactly the type of material that the experiments needed in quantities large enough to provide shielding for multiple detector systems. The lead had been underwater for the precise amount of time needed to allow radioactive contamination to decay while preserving the material's structural integrity. The ethical dilemmas surrounding the use of archaeological artifacts for scientific purposes created unprecedented challenges for both communities. Archaeologists had spent decades developing professional standards that emphasized preservation of cultural heritage over other considerations. The idea of melting down irreplaceable Roman artifacts to build modern scientific equipment violated fundamental principles that governed their field. Professor Donatello Salvi, who led the archaeological team, described the decision as painful and worried about the precedent it might set for future interactions between archaeology and other disciplines. The physicists faced their own ethical concerns about using historically significant materials for experimental purposes. The XENON collaboration recognized that their request represented a fundamental departure from normal scientific practice. They were asking archaeologists to sacrifice unique artifacts that could provide insights into Roman industrial practices and trade networks. The physicists had to balance their scientific goals against the cultural value of preserving these artifacts for future historical research. The decision required careful consideration of whether the potential scientific discoveries justified the loss of irreplaceable historical materials. The collaboration between archaeologists and physicists required both communities to step outside their normal professional boundaries and learn to work together effectively. The archaeologists had to understand the technical requirements that made the Roman lead essential for dark matter detection experiments. The physicists needed to appreciate the historical significance of the materials they were requesting and the cultural value that archaeologists placed on preserving these artifacts. Both groups had to develop new protocols for sharing responsibility and ensuring the collaboration served the interests of both scientific disciplines. The negotiations to acquire the Roman lead required months of careful discussion between the archaeological and physics communities. The physicists offered to provide funding for the excavation and preservation of the shipwreck site, enabling the archaeologists to recover and study the full cargo of over 30 metric tons of lead ingots that had been scattered across the seafloor. The archaeologists agreed to provide access to the least well-preserved ingots for scientific use, allowing the most historically significant specimens to be preserved for future study. Both sides recognized that the collaboration offered benefits that neither could achieve independently. The agreement established a precedent for future partnerships between archaeologists and physicists that balanced scientific needs with cultural preservation goals. The physicists committed to using only the minimum amount of lead necessary for their experiments and to sharing their analytical results with the archaeological team. The archaeologists retained control over the most important artifacts while gaining resources to support their research programs. The collaboration created a model for how different scientific disciplines could work together to achieve goals that neither could accomplish alone. The technical challenges of converting Roman lead ingots into modern experimental shielding required expertise from both archaeological and engineering communities. The physicists needed to understand the historical context of the lead's production to ensure that their processing methods didn't introduce new sources of contamination. The archaeologists provided crucial information about the lead's composition and manufacturing techniques that helped the physicists design appropriate handling procedures. The collaboration required both groups to develop new skills and approaches that combined historical knowledge with cutting-edge technology. The success of the Roman lead collaboration opened new possibilities for partnerships between archaeology and other scientific disciplines. Museums began working with materials scientists to develop better preservation techniques for ancient artifacts. The collaboration demonstrated that the intersection of historical research and modern science could produce discoveries that neither field could achieve independently. The carefully negotiated agreement had resolved the ethical concerns and established a framework for collaboration. Now came the most challenging part, converting priceless historical artifacts into the precision components that modern physics demanded. The ancient lead's new mission. Physicists recast ancient lead into 6-centimeter thick shield layers at XENON, preserving history and enabling record sensitivity. The transformation from Roman trade cargo to scientific equipment required the team to become metallurgists, carefully planning how to convert ancient artifacts into precision-engineered components. They needed to extract maximum shielding capability from the Roman lead while minimizing the amount of ancient material they would have to destroy. Each ingot represented a piece of Roman industrial history, but it also contained the exact properties that modern physics demanded. The underwater aging process had fundamentally altered the Roman lead's atomic structure in ways that made it perfect for particle physics applications. During the 2,000 years beneath the Mediterranean, radioactive isotopes naturally present in the lead had undergone decay processes that reduced their concentrations to negligible levels. Lead-210, the isotope that makes modern lead unsuitable for sensitive experiments, has a half-life of 22.3 years. The Roman lead had experienced nearly 90 half-lives of decay, reducing its lead-210 content to levels that were virtually undetectable by even the most sensitive instruments. The chemical environment at the bottom of the Mediterranean had provided additional benefits beyond simple radioactive decay. The constant temperature and pressure conditions prevented the types of chemical reactions that could introduce new contaminants into the lead. The lack of oxygen in the deep-sea environment eliminated oxidation processes that would have altered the lead's surface chemistry. Most importantly, the water itself had shielded the ingots from cosmic ray bombardment, preventing the nuclear reactions that create radioactive isotopes in materials exposed to space radiation. The 2025 advances in shield design ink lessons learned from the Roman lead experiment into new approaches for protecting sensitive physics experiments. The Cupid upgrade to the core experiment utilizes refined shielding geometries that maximize the effectiveness of the ancient lead while minimizing the amount of material required. Advanced computer modeling allows physicists to optimize shield configurations before construction begins, ensuring that every gram of Roman lead provides maximum protection against background radiation. These computational tools represent a significant improvement over the trial and error approaches used in earlier experiments. The balance between archaeological preservation and scientific progress required careful negotiation between two communities with fundamentally different priorities. The archaeologists needed to document the ingots' historical significance before allowing their destruction. The physicists contributed funding that supported the continued excavation of the Shipwreck site, enabling the recovery of additional artifacts that would have been lost to natural deterioration or unauthorized salvage operations. The technical specifications that made the Roman lead invaluable extended beyond its low radioactivity to include its chemical composition and physical properties. The lead contained trace amounts of silver and other metals that were naturally present in the Roman ore sources. These impurities actually enhanced the lead's shielding properties by increasing its density and improving its ability to absorb gamma rays. The ancient smelting processes had produced lead with a grain structure that made it easier to work with during modern processing, allowing the physicists to create shield components with the precise shapes and tolerances their experiments required. The success of the Roman lead experiment inspired similar collaborations between archaeologists and physicists around the world. Other underwater archaeological sites began to attract attention from materials, scientists seeking sources of low background materials for sensitive experiments. The protocols developed for the core project became models for future partnerships that balance scientific needs with cultural preservation. Goals. These collaborations demonstrated that interdisciplinary cooperation could achieve results that neither field could accomplish independently. The experimental setup using Roman lead shielding pushed the boundaries of what was possible in particle physics research. The shield components fit together with precision that would have impressed the original Roman metalworkers, creating a barrier that blocked background radiation while allowing faint signals from potential particle interactions to pass through to the detectors. The ancient lead's journey from Roman commerce to modern science represented a connection across time that linked ancient industrial practices with contemporary efforts to understand the fundamental nature of reality. The unknown detector now operates with unprecedented sensitivity, protected by lead that witnessed the rise and fall of empires while slowly purifying itself at this moment. The Roman merchants who loaded those ingots onto their ship could never have imagined that their cargo would one day help scientists probe the deepest mysteries of existence. The lead that once served Roman construction projects now shields experiments designed to detect the universe's most elusive components. This transformation represents more than just clever recycling of ancient materials. The Roman lead enables scientists to search for answers to questions that challenge everything we think we know about reality. The same lead that helped build Roman aqueducts and buildings now protects instruments capable of detecting individual particle interactions that occur less frequently than once per year in tons of target material. The precision required for these measurements pushes the boundaries of what human technology can achieve. The ancient lead has found its ultimate purpose in the service of human knowledge, protecting experiments that could revolutionize our understanding of the cosmos. The Roman ingots have become guardians of scientific discovery. Their 2,000-year journey from Mediterranean seafloor to underground laboratory representing one of the most unlikely collaborations between past and present ever achieved. Their story connects ancient commerce with modern physics in ways that reveal the unexpected threads linking human civilization across millennia. The stage is now set for discoveries that could transform our understanding of existence itself. Everything around us represents only a tiny fraction of what actually fills the XENON detector now operates as the most sensitive dark matter hunting instrument ever constructed. Dark matter comprises 85% of the universe's total mass, remaining invisible except through its gravitational effects on visible matter, and recent results from the Lux Zeppelin experiment have excluded WIMP dark matter particles above 9 GeV. The Roman lead shields surrounding the XENON chamber create the pristine conditions necessary for detecting these elusive interactions, blocking background radiation that would otherwise overwhelm the faint signals scientists hope to measure. The gravitational evidence for dark matter's existence comes from observations that should be impossible if only visible matter existed in the universe. When astronomers study rotating galaxies, they find that stars on the outer edges move too fast to be held in orbit by the gravity of visible matter alone. Something invisible must be providing the additional gravitational pull needed to keep these galaxies from flying apart. That something outweighs all the visible matter in the universe by more than 5 to 1, creating cosmic scaffolding upon which ordinary matter assembles into the structures we observe today. Computer simulations reveal how dark matter forms vast filaments stretching across space, with dense nodes where matter accumulates to form galaxy clusters. These simulations accurately predict the distribution of galaxies we see when we look deep into space, but only when they include 5 times more dark matter than visible matter. Remove the dark matter from these models, and the universe becomes a sparse, uniform soup with no galaxies, no stars, and no planets. The cosmic web of dark matter creates the framework that allows the universe's architecture to exist. The connection between dark matter detection and the matter-antimatter asymmetry puzzle runs deeper than most people realize. Some theoretical models suggest that the same physics responsible for creating the tiny imbalance between matter and antimatter in the early universe also governs how dark matter particles interact with ordinary matter today. If these models prove correct, detecting dark matter could provide crucial insights into why the universe contains matter instead of pure energy. The experiments searching for dark matter particles might simultaneously solve 2 of the most fundamental mysteries in cosmology. The XENON experiment achieved a 5-fold improvement in background suppression compared to its predecessor, establishing new limits on how dark matter particles might interact with ordinary matter. Based on 97.1 days of operation, XENON demonstrated world-leading sensitivity that surpassed all previous experiments in its ability to detect hypothetical dark matter interactions. The ancient Roman lead provides the ultra-low radioactive contamination levels that make this unprecedented sensitivity possible, creating detection conditions that modern materials simply cannot achieve. When a dark matter particle theoretically collides with a xenon nucleus, it transfers only a tiny amount of energy, producing flashes of light and electrical signals so faint that even microscopic amounts of background radiation can overwhelm them completely. The Roman lead blocks this background radiation by providing shielding with contamination levels, orders of magnitude lower than contemporary materials. The 2,000-year underwater aging process reduced radioactive isotopes to virtually undetectable levels, creating the pristine environment necessary for detecting individual dark matter interactions. Scientists have expanded their search beyond traditional WIMP candidates to explore other potential dark matter particles. The Tesseract experiment targets particles about 100 to 1,000 times lighter than WIMPs, using transition-edge sensors that operate at temperatures around 8 millikelvin. These sensors can detect energy deposits as small as a few electron volts, opening new territory in the search for low-mass dark matter particles. Tesseract's initial tests found no dark matter signals, but established unprecedented sensitivity for detecting interactions involving extremely light particles. Axions represent another promising dark matter candidate that requires entirely different detection methods. These hypothetical particles would interact with magnetic fields in ways that convert them into detectable photons. Researchers have developed techniques using squeezed coherent states of light to amplify the conversion probability between photons and axions, potentially leading to more sensitive detection experiments. Teams of scientists have made significant progress toward using quasiparticles to hunt for axions, which could constitute a significant fraction of dark matter. The theoretical models guiding dark matter searches have evolved significantly based on the latest experimental results. Supersymmetric theories predict specific ranges of masses and interaction strengths for dark matter particles, but recent known results have forced theorists to explore alternative scenarios. Some models now focus on dark matter particles that interact primarily through forces other than the weak nuclear force, requiring new experimental approaches that go beyond traditional xenon-based detectors. Multiple experiments around the world are converging on similar sensitivity levels, creating opportunities for cross-validation of any potential discoveries. The core experiment in Italy, also protected by Roman lead shielding, searches for neutrinoless double beta decay while maintaining sensitivity to certain types of dark matter interactions. The combination of results from different detector technologies and target materials provides complementary information that strengthens the overall search strategy. Recent detection candidates and anomalies have generated excitement throughout the dark matter research community. Several experiments have reported events that could potentially represent dark matter interactions, but these signals remain below the statistical threshold required for definitive discovery claims. The XENON collaboration has observed excess events in their electron recoil data that could indicate new physics, though the significance falls short of a discovery-level detection. The success of using ancient Roman lead for dark matter detection has demonstrated that archaeological materials can enable scientific breakthroughs that would be impossible with modern materials. The underwater preservation process created lead with radioactive contamination levels that 21st century technology cannot replicate, regardless of the purification techniques employed. This unprecedented collaboration between archaeology and physics has opened new possibilities for future experiments that require materials with properties that only time can create. The future of cosmic archaeology. Scientists around the world now recognize that their most ambitious experimental goals may depend on materials that have been aging underwater or underground for centuries. The success of the Roman lead experiment has created unprecedented demand for ancient materials that possess the ultra-low radioactive contamination levels required by cutting-edge physics research. The 30 tons of Roman lead that enabled breakthrough sensitivity in dark matter detection experiments represents just the beginning of what could become a systematic search for archaeological materials with unique scientific properties. The 2025 landscape of particle physics experiments reveals a field pushing toward detection sensitivities that modern industrial materials simply cannot support. The U.S. Department of Energy has committed $71 million in funding across 25 high-energy physics projects, with the aim of leveraging quantum information science to explore fundamental questions about the universe. These experiments require shielding materials with background radiation levels that are orders of magnitude lower than what contemporary manufacturing processes can achieve. The funding supports development of quantum sensors and detection technologies that will need even more sophisticated protection from environmental interference than current experiments. The success of the Archaeological Physics Partnership that produced the Roman lead shielding has inspired similar collaborations worldwide. Teams of scientists are now actively searching for underwater archaeological sites that might contain metals suitable for scientific applications. Shipwrecks from different historical periods offer materials with varying degrees of radioactive decay, allowing researchers to match specific archaeological finds with the requirements of particular experiments. Bronze Age shipwrecks might provide copper with different contamination profiles than Roman-era sites, while medieval vessels could offer iron with unique purity characteristics. International protocols for responsible acquisition of ancient materials have evolved rapidly to address the ethical complexities of these partnerships. The archaeological community has developed guidelines that require extensive documentation of historical context before any materials can be transferred to scientific applications. These protocols mandate that physicists must demonstrate that no suitable modern alternatives exist and that their proposed research addresses questions of fundamental scientific importance. The agreements also ensure that archaeological teams receive adequate compensation and resources to support their own research programs. Experiments like Tesseract demonstrate how archaeological materials continue to enable new frontiers in physics research. Tesseract is planning to relocate its experiment underground to the Modin Underground Laboratory in France to reduce cosmic interference, with operations expected by 2029. The experiment will search for dark matter particles as light as 10 MeV, requiring detection systems with sensitivity levels that demand the purest possible shielding materials. Ancient metals could provide the background suppression necessary to explore this previously inaccessible mass range for dark matter candidates. The growing intersection of history and high-energy physics has created entirely new fields of interdisciplinary research. Material scientists now study ancient metallurgy techniques to understand why certain historical processes produce metals with properties that modern industry cannot replicate. Archaeologists are incorporating materials analysis techniques developed for particle physics to gain new insights into ancient trade networks and manufacturing practices. The collaboration has generated research opportunities that neither field could pursue independently. The integration of quantum technologies with particle physics represents another frontier where ancient materials could play crucial roles. The Department of Energy is funding projects that use quantum information science technologies, including superconducting qubits and atomic sensors, to enhance experimental sensitivity. These quantum-enhanced detection systems require environmental isolation that exceeds even the demanding requirements of current dark matter experiments. Ancient materials with centuries of radioactive decay could provide the ultra-quiet environments necessary for quantum sensors to achieve their theoretical performance limits. Current discoveries continue to reveal new applications for archaeological materials in modern science. The Resnova project uses Roman lead recovered from shipwrecks to shield detectors, searching for neutrinos from astrophysical sources. The Herald and Spice detector modules are being developed to diversify detection methods and cross-validate potential dark matter signals, each requiring specialized shielding materials with specific purity characteristics. These projects demonstrate how ancient materials enable multiple experimental approaches to fundamental physics questions. The search for materials extends beyond shipwrecks to include archaeological sites on land that might have preserved metals under conditions that prevented contamination. Ancient mines that were sealed and abandoned could contain metals that have been isolated from cosmic radiation for centuries. Historical smelting sites might yield slag or byproducts with unique chemical compositions suitable for specialized applications. The systematic exploration of archaeological materials for scientific applications has become a recognized field that combines historical research with materials science. The economic implications of using archaeological materials for physics research have created new funding models that bridge scientific and cultural preservation goals. Physics experiments provide resources for archaeological excavations while gaining access to irreplaceable materials. These partnerships generate scientific discoveries that serve both physics and historical research communities, justifying the investments required to develop and maintain these unique collaborations. The XENON experiment continues to operate with the unprecedented sensitivity that only the Roman lead shielding makes possible. The ancient metal blocks gamma rays and other forms of radiation that would otherwise overwhelm the detector's ability to distinguish genuine dark matter interactions from background noise. The 2,000-year underwater aging process that reduced radioactive contamination to virtually undetectable levels has enabled scientists to probe deeper into the fundamental mysteries of existence than ever before possible. This extraordinary collaboration between archaeology and physics has demonstrated that the answers to our most profound scientific questions might require resources that transcend the boundaries of any single discipline. The marriage of ancient preservation and modern detection technology has opened new pathways to understanding reality itself. The Roman lead that once served commercial purposes in the ancient world now guards the most sensitive scientific instruments humanity has ever constructed, protecting experiments that could reveal why the universe contains anything at all. The convergence of ancient preservation and modern detection has produced results that validate this extraordinary collaboration. XENON achieved a 5-fold improvement in background suppression compared to previous experiments, establishing world-leading sensitivity in the search for dark matter interactions. This breakthrough became possible only because Roman lead provided radioactive contamination levels that modern materials cannot match, no matter how sophisticated the purification techniques employed. A Roman merchant sailing the Mediterranean 2 millennia ago had no idea his lost cargo would become essential to this scientific achievement. The lead. Ingots that sank off Sardinia were destined for construction projects that never happened. Instead, they aged underwater for 2,000 years, allowing radioactive isotopes to decay to levels that enabled the most sensitive particle physics experiment ever constructed. The story connects ancient commerce with modern physics in ways that reveal how preservation, chance, and human curiosity can converge to address the universe's most fundamental mysteries.